No, I have one here. Thank you. Okay. Well, my name is Mads Frederik Madsen. I come from the IT University of Copenhagen, and I've written this paper in collaboration with a few others. Mikkel Gau, Trondo Høgnason, Malte Kirkbro, and Søren de Bois from IT University also, as well as Thijs Slats from Copenhagen University, which is also present. So the setting we're in here is collaboration among adversaries on workflows. At the moment in Denmark, there's a big conflict on salary on the public area, especially with teaching. And this conflict is handled by two major umbrella organizations called Danish Unions and Danish Employees, which will be our example case in this presentation. But first we need to understand the basics of workflows. So when we talk about workflows, we talk about models of business procedures. That is, how do you make a car? We need a model of which process comes before other processes in order to achieve like a single core, right? Single car, right? And this becomes really interesting when we talk about distributed workflows. That is, workflows where we have multiple participants that need to work together in some area in order to achieve the goal of this workflow. Because this enables them to do the activities, the processes concurrently. Well, and one of the okay, I'm sorry. So the setting here is that we have some distributed workflow, and the organizations that are working together, that are collaborating on this workflow, are adversaries, or they at least have adversarial tendencies. So they have an agreed upon workflow. They need to achieve some goal using a workflow, but sometimes they have conflicting interests in this workflow, and can have a small incentive to follow the procedure that they have agreed upon. And the example case here is, as I mentioned, is Danish Unions and Danish Employees, which handles disputes between employers and employees in Denmark, such as unpaid salary and mass firings, or as this is the case right now, agreeing on salary and benefits for the employees. Sorry. The question here is, how do we stop one participant from disrupting the workflow, doing something else or in another order than was intended and agreed upon, when the other participant has an especially strong case, for instance in the case of unpaid salary, right? How do we prevent Danish employees from delaying the process or disrupting the process? Traditionally, this is solved by using a third party, most often a lawyer, who will record every action that is taken, as well as verify that they actually have been accomplished. But that can be quite expensive, as well as difficult to agree on which third party they should use. They are adversaries, right? So how do they agree on which third party they should use? Instead, what we are trying to do is oh no, we'll take that later. Okay, so this is the example workflow we'll be going through. We have Danish unions and Danish employers, where this is a simplified version of how they arrange a meeting. We have Danish unions. They have agreed that Danish union will propose the first meeting date, and then Danish employers can either accept this or they can make a new proposal. They can keep on doing this. Then Danish unions can propose a date, and Danish employees can accept or make a new proposal, and they can keep on doing this. But at some point, they have to accept. The other party has to accept one meeting date. And when they have accepted this meeting date, we cannot have more acceptance of previous proposals, and we want to enable the meeting to be held. Quite simple. And after the excellent introduction to Ethereum and smart contracts, some of you might notice that this is actually a contract that the participants are agreeing on, or that they want to. So this is a contract that they want to work together on achieving, right? And the idea here is that we want to use a smart contract to implement this to avoid the third party. But first we need some model to some way to model these workflows. And for this we have chosen the dynamic condition response graphs, also called DCR graphs, which are essentially a model for a notation for modeling these workflows, and they consist of two abstract entities. There are events represented by these squares, tan squares. They are also called activities, as well as relations, which are modeled by these arrows here. So let me just the events or activities each have states. There are three different state variables that can be that represent the state of an event, which are it can be included or not included, it can be pending or not pending, and it can be executed or not executed. The relations here, the arrows, are static. That there's no change in the relations. Instead, there are two abstract views of the relation. There are the one that constrain the workflow and the one that affect the workflow or other events. That is, whether an event can be executed is constrained by the constraining relations, and when an event with one or more affecting relations are executed, it will affect the state of another event. So we have these two notions: enabledness, can the event be executed, which is related to the constraint relations, right? As well as the execution of an event, which will change the state of the event itself and any events on the other end of a affecting relation. So let's go through the example I did before now as a DCR graph. We have 5 events. Danish union can propose a meeting date. Danish employers can propose a meeting date. They can both accept the other's proposal, and at last they can hold the meeting. The event states here are represented as these are included, not pending, not executed, while the accept events are excluded, that they are not included, which is represented by this dotted line here, which means that they are not enabled. They cannot be executed from the beginning of this workflow. We also have a pending state on this hold meeting event, meaning that the workflow is not considered complete until the hold meeting event has been executed or excluded. So the Danish unions and Danish employers agreed that Danish unions will propose the first meeting. We model this as a constraining relation. This is called the condition relation. From Danish unions' proposed meeting date to Danish employers' proposed meeting event, which essentially means that this one has to be run before this one can be run or executed. The workflow also included that that there have to be proposed a meeting date before one can be accepted, right? And this was modeled. This is modeled in the DCR graph as having the event states being excluded and then including them with an affecting relation here from the proposed from Danish unions and Danish employers' proposed events. We also say that when we have proposed some meeting dates, at least one of them must be accepted, and we represent this by the affecting response relation here, which will set the opposite events as pending when the proposed events are run. We want to exclude concurrent runnings of accept events. That is, this was the point about we don't want them both to accept the other's proposal at the same time, because if they do that, then there's no consensus and there's no agreement on when they're going to meet. So you can only run a single event, which is represented by excluding, that is, setting the included variable to false on the accept events when these are run. And lastly, when the accept events have been executed, we want to be able to hold the meeting, which is represented by this constraining relation called the milestone relation, meaning that neither of these must be pending. and include it while before we can run this. Okay, it's quite a lot of DCR graphs, but the idea here is that we now have a model for modeling these workflows. We have a notation for modeling these, and we can use this to implement a system as an Ethereum smart contract. And when we do this, we have to recall that we want to solve the problem where the collaborators are adversaries. So if such a system, when we implement such a system, we must guarantee workflow correctness. That is, that none of the participants can violate the agreed upon workflow, as well as the consensus on history. That is essentially non-reputability. That none of the participants can later come and say that we didn't know that it was executed, or I didn't execute this activity, and I don't know this. I didn't know the state at the moment. So we already had some essentials on Ethereum. I just want to remind you, it's this distributed platform that runs smart contracts, which formally means that it's a computer protocol for enabling and facilitating an actual contract, which is implemented on Ethereum as a more or less self-contained set of functions that affect a self-contained state. And this is done by invoking the set functions of the smart contracts on the Ethereum virtual machine, and these functions is invoked by making transactions on the Ethereum blockchain, right? And since it uses a blockchain and each function is invoked by a transaction, and the blockchain gives consensus on transaction history, Ethereum essentially just gives us consensus on the execution of the smart contract, which also translates to consensus on the execution history of a workflow. We just have to keep in mind that when we use this blockchain, the function invocation, the running of the function has an associated cost, because we essentially just transfer ether, right? And this is measured in the denomination of gas. Each instruction on a smart contract has an associated gas cost, which is, it has no inherent value as such. The value is given by the transaction, where the transactor, the one sending the transaction, can specify how much ether he or she is willing to pay per unit of gas. So the point here is that the gas cost here is constant, given the same state of the contract and the same parameters of the function invocation. Yes. So the idea here is we can take a DCR graph, model it as a smart contract, and put it onto the Ethereum blockchain. And then we are given automatically workflow correctness by the DCR graph model and consensus on the execution history by the Ethereum blockchain. However, it has this notion of cost. So we did a small proof of concept of this, of having a single DCR graph running on a single smart contract. And we observed that the predominant cause of cost was initializing the workflow. That is, having the data related to the workflow, put it onto a smart contract, and then putting it onto the blockchain. This is by far the most costly operation. There were also some costs associated with executing an event and checking whether the event was enabled.
So you mean the contract code, just to load the contract code?
To publish it. To publish the contract code, yes. Mm-hmm. You can actually see it here. So this is the initial, quite kind of naive smart contract implementation we did, where making the smart contract and loading the functions and the initial state of the workflow had the gas cost of a bit more than 2 million gas. It should be noted that these USD values are not correct anymore. It's about tripled since we did this. So this is we did with the workflow that I described to you before, right? DCR graph with the Danish units in Danish employers. And as you can see, it's by far, the cost is really dominated by the initialization of the workflow. So we wanted to do some cost reduction because the entire reason, one of the reasons we did this was we wanted to avoid a third party which could be difficult to agree on and could be quite costly, right? So one of the arguments for doing this is that we want to reduce cost. So we had some. So this is the approach we took to limiting the cost of running this DCR graph. So in order to avoid this contract creation cost. So the essential realization here is that the act of creating a smart contract, regardless of what data and what function it holds, has quite a big cost. So what we did was we modeled a smart contract which can hold multiple workflows and dynamically add new workflows to it and store all of them in a single contract. We also wanted to limit the execution costs bounded, really, and we did this by storing the activity states and relations as bit vectors. I'll go into details on that in a moment. But doing this also enabled us to pack the data we did that was included in transactions on the Ethereum blockchain. So this bit vector implementation. You might recall that I mentioned that the smart contract functions are run on the Ethereum virtual machine. And this Ethereum virtual machine, as a default, uses computations or uses 256-bit words as computations, for computations. And we realized that we can represent this, the state of a DCR graph as 3 256-bit words. So that is words that, or a bit vector if you want, representing which of the activities were included, a word representing which of them were pending and which of them were executed as well. And then we can reduce each event execution to a few bitwise operations. I'll show you those in a moment. As well as I mentioned, we can pack initializing the workflow into just these 3 bit vectors, as well as bit vector representations of the relations of the DCR graph. So this is the function on the optimized smart contract, which checks a function's enabledness. And I've marked so you don't need to understand this really, but the important thing is that all the essential operations for checking whether an event can be executed are done with these 6 bit operations.
Solidity?
Yes, this is Solidity, yeah. And the execution function, that is the function that changes the state of a DCR graph, can be reduced to these 9 bit operations, marked in red. Okay. So, having optimized this, we saw the following results. We reduced the initialization costs by an order of magnitude from around 2 million to around 700,000 gas. And we reduced, which was predominant, right? You might notice that the execution of these events here have increased slightly in cost, which is mostly because there's a bit of overhead doing this bit vector operations, but also because this workflow doesn't really do justice to the optimized version here. When we have these this execution of an event in the naive implementation, when you had a state changing relation to another event, for instance, you would go to the other relation and then change the state of that event. However, in the bit vector operations, in the bit vector implementation, what we did was we changed the entire state of the entire workflow when the event was executed. So if you had several of the same type of relation on the same event, you would do all the state changes in a single bit vector operation. Also, the optimized version here is. So, I'll come back to some more about this in a moment. There's another observation that we made when we did this, which is that it seems that we have, since we induce cost on executing a DCR graph, someone must pay for an execution. And traditionally in DCR graphs, there's no notion of ownership of a relation. However, each relation induces some cost when executing an event. So now we had to define some sort of ownership of this relation. So this is the point we came up with. The constraining relations. This is the condition, the milestone, induced cost on the constrained event, while the affecting relations induced cost on the origin event. So I'm running out of time, so I'm just going a bit quickly here. But what you'll notice is that if we take this ownership into account on the original workflow, you see that this event here is the only event that has three relations associated with it. We have this constraining relation and these two affecting relations. And if you look at the cost reductions, you'll see that this actually this is the only one that decreased in gas cost, which is indicative that the more relations an event has, the cheaper or the less increase you'll see when compared to the naive implementation. Yes. So, in conclusion, a DCR, we set out to design a system where we could avoid this third party when we had collaboration among adversaries on DCR graphs, and it's certainly doable, and it can be done by using Ethereum and implementing DCR graphs as a smart contract. However, it's important to notice that everything that you do on Ethereum, every transaction that's made, has an associated cost. And while you can reduce this cost with the methods I introduced here, you can never get completely rid of it. Yes, that's it. Thank you. Oh, by the way, if you want to try it live, we have a proof of concept distributed app available at this URL. Yes.
Could you go back to the cost slide?
Yes, sure.
Sorry. So this 14 is $14, right?
This is $14.
So 14, okay.
Yeah, at the time of writing, which would be about triple now.
And
Yeah.
so it's more expensive to pay as party, right? Much more expensive to pay as party. Do this,
So
right?
if it's a law, you're saying.
Yeah. Yeah.
So,
Yes, it is. But
so like even with this $14, I mean,
it's still pretty cheap. Yeah.
right? I mean,
Yeah. Yes. I think you were first, yeah?
So I see your research is more about to optimize the cost reduction, right? For
Yeah.
Writing smart contract on Ethereum. So by basically converting the logic into bit operation, right?
Yeah.
So this is your example is a relatively sort of simple workflow, right? Basically changing state from one state to another, right?
Yeah.
So imagine if we have a real life workflow, right? It's usually more complicated. You need to do a lot of logic, and by putting complicated workflow on a regular smart contracts in Solidity, it's already not straightforward because of this data type is all cumulative, and there's no modern language support of fancier data type, right? Now you're trying to put another layer of hardship, trying to change all this thing into bitwise operation, right?
Yeah.
How do you see the practicality of this optimization, right?
So as I understand your question, it's that you have difficulty in translating a real life workflow into a DCR graph, because what we did here was we made DCR graphs which should be completely. So we made an implementation which could represent all DCR graphs in principle. So your question is whether it's practical to to translate a real-life workflow to a DCR graph?
No.
No. Okay.
My question is about, so the DCR graph is basically the state change, right?
Yeah.
Of a real problem, right?
Yes.
But now you are, instead of writing regular code, like
Yeah.
checking to see if the current state is this, and then now you have an input from the DE or DU, and they say yes or no, and then you change to another state, right? Like
Yeah.
you write in a regular program, you do if then else stuff like that, right? But now you're doing big operation,
Yeah.
trying to check the current state. You basically have a free word variable, and then basically trying to see the current state, and then use while operation to change to another state, right?
Yeah.
So basically, you're changing a readable program to a sort of non-readable program. It's harder to.
No.
It's not intuitive, right? It's
Okay.
not intuitive to a business workflow owner, to an application developer.
No, it's not intuitive for a business process owner. That's completely true. But DCR graphs should be quite more intuitive for a business owner, right? If they have the proper notion, understanding of workflows to begin with. And the entire thing here is that we've taken a DCR graph and then we've done different implementation of it. And all you really need to understand as a business owner is that you can represent it. You can represent your workflow as a DCR graph, and this is the lowest cost implementation that we've been able to find of this. Does that make sense? Does that answer your question?
I can help you all.
Yeah.
My question was rather similar.
Yeah.
Somewhere you are transforming your graph inside a vector,
Yeah.
and you were checking from one vector that you had that.
Yeah.
My question is, have you tried to verify that your vectorized workflow, because more or less you are in vectorized workflow that you store somewhere, there is correctness between what I was expecting and what your smart contract will implement? That's a huge assumption, is that what your smart contract will enforce is what I was specifying.
Yes.
How do you verify that? Have you some way to prove that?
Well.
Else we will end up with a lawyer which will have to ask experts to verify the problem.
Yeah. So you're asking whether we have verified our own code as Solidity code as.
As a user, if
Yeah.
I would be a user, have had some way to verify that what I was specifying somewhere by words,
Yeah.
how it will start, or by a graph which will not be this one, will end up with something in a smart contract which works. As long as we don't have that on that,
Yeah.
there is a risk of, with all the smart contracts, to have bugs, vulnerabilities, and so on.
Yeah.
And you are not better than when I have a lawyer which will come with that. Cost, by the way, the cost will always come when somebody will fail.
Yeah.
And then you will have the cost of the lawyers, not the cost of the transaction, but the cost of the lawyers. As long as everybody is lawful, perfect.
Yeah.
But my question is really, do you work on that part between a specification on verifying formally that your implementation is enforcing what was specified?
So I'm not, but maybe Thijs has some.
So, I mean, you need to trust the compiler, right? And if you look at, first of all, you need to trust the semantics of your workflow. And if you look at the code, it's really simple. So it's really, we didn't verify this formally. It is like 20 lines of code. You don't really show the compiler from.
I understand that your code was probably simple.
Yeah.
But it's somewhere, at one moment, I have to transform my graph inside vectors.
Sure, but
And that is not just 20 lines of code.
well,
There is something which you are doing either by hand, or you are doing by a code which is far more complex.
no, it's not so complex because essentially the graph. Think of the.
And I think here, not a simple graph, but as the gentleman was asking, let's go in real world things where we have large workflows on very complex things. I'm even not quite sure that a 3 words vector would be sufficient.
So.
First of all, right? Sure. The size of the word means that we can only support 260.
56.
56.
Yeah.
But then compiling the graph to these bit vectors is very straightforward because it's just a mapping of the activities to places in the bit vector and it's totally 0 or 1 based on the state, right? So that's not really complicated. Also, mapping the relations is just mapping to a matrix.
Good.
Between which then the big question is, does the graph actually represent the real workflow in real life? And I mean, that's a much more complicated, but that we should discuss. I think that's